Ah, yes. So you guys will tell me when to start, right?
Share your screen and start, please.
Oh, I can start?
Yeah, please.
Yeah, all right. Your audio is a little uh,
Yeah, I
funny.
will turn off the camera. Perhaps this will help.
Yeah, okay. So I think I was told to start, then I
Yes,
shall.
please.
Then I shall. Hello, everyone. I'm Caren Marzban, um, University of Washington, uh, split between two departments, a Department of Statistics and a place called the Applied Physics Lab. All right, so let me start with a warning. This talk will be a little different from what we've seen in this school. Chances are it's pretty different from anything you may have seen before. Um, it's very light on math, but very heavy on concepts and jargon terminology. So if you like that, if you like little math and lots of concepts and words, you're in luck. But it does catch a lot of people off guard that, wait, what's this guy talking about? This doesn't sound familiar at all. Well, I did warn you about this. So stay with me. I hope it'll all go seamlessly, but we'll see. Okay, let's start with a motivational example. Um, Suppose we have three models, three NWP models, NSEP, WRF, and COAMPS, and we're trying to compare them. Well, you might think it's easy. I'm just going to run NSEP and run WRF, run COAMPS on anything, a temperature forecast, precip, low-level wind, whatever, and look at the three scores and do some tests, and we're done. Well, wait. By the way, the score, I'm calling it a performance or skill score. This is just a generic word for any performance score and any measure of quality. Could be probability of detection, could be ROC, AUC, anything. Just pick your favorite score, and I'm just going to call that Y. Well, what if you started wondering, okay, what if there's a difference between these three models, depending on whether they're verified on land or on water? Okay, so we just introduced another factor into the question, the land-water question. What if you wonder if there's a seasonal factor? Maybe one model does better in hot seasons, another model does better in cold seasons. Well, we just brought in another factor, season. I don't know what to call this land-water factor. We'll just call it X2. So the question slowly became bigger. We're now making lots of comparisons between skill scores or scores. And you might think I made up this list to make it intentionally complicated, but a professional meteorologist colleague of mine by the name of Scott Sandgaith tells me that a place called the Navy Research Lab routinely, NRL in the US, routinely uses factors like this to assess and compare different models with each other. Okay, so it's not made up, it's a realistic situation. The last one, X8, I added in by hand, I have to confess, because I wanted to have 8 factors for reasons that you'll see. By the way, I use this term factor. Here we go with jargon. A factor is not a lay word, is not a general term. It's a specific term for a categorical variable. Because see, if you look at this x1, x2, all these things that I've called x1, x2 to suggest they're variables, they're not continuous things. They don't take numerical values. They take these categories, WRF, NSEP, COAMPS, land, water, right? These are all 8 of these variables are categorical variables, and hence they're called factors. So here's one bit of jargon that you'll hear me use a lot. By the way, all the jargon that I'm going to talk about today is specific to this very large topic called experimental design. Okay. The other piece of jargon is the different levels that the different values that each of these variables takes, like land, water for X2, or tropical mid-latitude polar for X4. These levels are called levels, okay? So not to be confused with pressure levels that you meteorologists talk about. So it's a little confusing, but again, it's standard jargon. Okay, so for example, X7 is 1, 2, 3. It's a 3-level factor, right? Okay, so two words, factor and level, that we've talked about. Okay, now when you start comparing things, in the first part of this talk, the talk is divided into 2 parts, so somewhat separate. In the first part, the question is very similar to the kinds of questions that Ian Joliffe talked about. How do we do statistical tests, t-tests, confidence intervals? How do we do inference to tell whether the true skill score between, let's say, 3 different models is the same or not? Okay, so that's the standard kind of question. If we have three models, so remember X1 is my NWP factor. So if it's NCEP, if it's WRF, if it's coamps, each one of those gives me a score, and I want to know if these are the same or not. Okay, so that requires 3 scores, 3 runs, right? I have to go run NCEP, I have to go run WRF, and I have to go run coamps to get these 3 scores. But the moment you start thinking about the other factors like land, water, so in other words, now you have to go run NCEP on land and on water. That just became 2 runs for NCEP alone, and another 2 for WRF and another 2 for coamps. Now we're looking at 6 runs and 6 scores that we have to obtain. Well, if you've ever obtained any of these scores, you'll know it's not easy to run NCEP on land and water and get 1 skill score. It might take hours, it might take days, depending on what exactly you're doing. So each of these 6 numbers, 6 scores, is hard to get. Okay, so it's a lot of scores, it's a lot of runs that we need to do, and this is just for 2 factors, X1 and X2. By the time you get to 8 factors, for example, the 8 factors we talked about, there are 8,640 scores you need to go compute. Okay, that's a lot of runs. In part 2 of this talk, I'll show you their tricks, methods, breaks we've gotten from nature that allow us to reduce this number, this 8,640, dramatically to a handful of numbers, handful of scores that we can run, and then you can answer all the questions you want. Okay, so here are the 2 parts of the talk. In the first part, I'll be talking about doing statistical tests, comparing multiple models in terms of all these different factors, season, land, water, whatnot. And in the second part, I'll talk about how you can reduce the number of runs you need to do to answer most of the questions you want to answer through these tricks that I'll be talking about today. Okay, so is the high-level picture of the talk clear? Oh, okay. I was told, I guess we were all told to keep the questions at the end, but please, I said it here, do feel free to interrupt. Just speak up. It's good practice. We're good? Okay. All right. Let's do it. Part 1. This will feel more familiar. If we only have two scores to compare, let's say NCEP on land and NCEP on water. Well, this is easy. We treat this score as the true mean of some distribution, and then you're in the realm of statistics, and then you look at Ian Jolis talks. Okay, I'm assuming that wasn't intended. You look at Ian Jolis talks, and you do a t-test, and we're done. Paired t-test, unpaired t-test, whatever. If we have three things we want to compare, three scores, three means, things get a little more complicated. You might say, well, I can compare them pairwise with t-tests, right? I can compare NSEP with WRF, that's one t-test, WRF with coamps, that's another t-test, and NSEP with coamps, that's another t-test. So that's three choose two, which is three t-tests, and then we can say we're done, right? We've made our comparisons. Here's a problem with this. The problem is referred to as the problem of multiple hypothesis testing. This is a phrase, standard phrase, problem of multiple hypothesis testing. And it can be shown that if you're comparing if you're doing lots of t-tests, like the three that we talked about here, the more t-tests you do, the probability of, I've called false alarm, but this is a little different from the false alarm, the way we think of it. The false alarm here is probability, the false alarm is finding a difference, like saying land and water are different, have different scores, when in fact they're not. Finding a difference when they're not. So it's also called a type 1 error. But meteorologists call that a false alarm, right? So if you do lots of t-tests, it's guaranteed the probability of finding a type 1 error, the probability of a false alarm is 1. It's guaranteed that you're going to find a difference between two of the comparisons that you've made when in fact there is no difference. Okay, so it's a dangerous road to get on. You don't want to do multiple tests. The solution to that is the ANOVA F-test. Okay, the beauty of the ANOVA F-test is that it will tell you in one test, you do one p-value, and it'll tell you if there is a difference or not. Okay, I'll get into more details in a minute. Then still, I'm talking high level, I'm getting hierarchically deeper and deeper into these topics. So when we start talking about part 2, this is the part where things are concept heavy. So I have to introduce new ideas, new concepts, new jargon, new everything. But the prize is really nice. Like I said, you're going to be able to reduce the number of runs, the number of comparisons you need to make drastically, okay, from astronomical numbers to a handful. But the math behind it is really simple, because ultimately it will come down to taking the difference between two numbers. We will be, in part 2, we will be talking about what are called magnitude of effect. So instead of comparing the statistical significance of an effect is a difference, okay? So it's a skill score on land minus skill score on water, for example, okay? That's called the magnitude of effect. If it's 0 right, in truth, then you say there's no effect, right? And how do you know if it's 0 or not? You do some sort of a statistical test. But in part 2, I'm not going to do any of the statistical test business. We just want to get a number itself, a point estimate, in other words, for this difference here. What is the difference in score between water and land? Okay, for let's say NSEP. In part 2, that will be the focus, and this will be the extent of the math that will show up there. So let's do this. Oh, the beauty of the F-test, I should say this. I call it a test of needle in haystack. because I hope you know what a needle in a haystack proverb is. Yeah, okay, if you don't, you have a mountain of little pieces of hay, and you know there's a needle in there. The question is, okay, where is it? Or is there a needle in there? Well, you can, by doing t-tests, you're going in there and checking every one of these hay strands to see if it's a needle or not. And if you do, as I said, if you do many of them, you're guaranteed to incorrectly say one of those needles, one of those hay strands is a needle. The F-test has this magical property where you do one test and it tells you if there's a needle in that haystack at all, if there is a needle in there or not, right? With one test. It's amazing. It's magical. So let me demonstrate. Learn to use it. And that's the takeaway from this whole part 1 of the lecture. Just do don't do too many t-tests. Do one F-test first. So to set the stage here, we go with the score. The score can be anything, mean square error, or AUC, whatever. I'm just going to call it Y. Okay. Typical math approach to things. Just give it a symbol. So ideally, we would want to have some variability of scores within the classes that we're comparing. So in this case, I'm taking one factor, X1. This is my NWP factor. So it takes 3 levels, NCEP, WRF, and COAMPS. Ideally, we want to get 2 or 3 different skill scores for each of these classes. And then you'll be able to do this one F-test, and it'll tell you if there's a difference between these 3 things or not, right? And by the way, there is an R code that I'm adding to this lecture. It's online. You can get it if you want already. It shows you how to do this F-test for this particular example here. The p-value that it returns turns out to be huge. So the conclusion is that we cannot reject the null hypothesis. We cannot reject this in favor of that, which means there's really no evidence that those 3 things are different. There's no evidence that the 3 models are different. The fast and furious way of saying that in this experimental design jargon is there is no NWP effect. That's how one says it. So when the p-value is big, you can't reject H0. It's too complicated. The quick and dirty way of saying it is that there is no NWP effect, which means all the NWPs are essentially the same. We don't know if there's a difference. Good? Okay. Let's bring in our other factor, X2. So X1 was the NWP factor, X2 was the land water factor. So again, suppose you have 3 skill scores or any score. These numbers are made up, by the way. Okay, I don't know what 136 is, but it's just some score. So what do we do? Well, again, easy. There's an F-test. There's a model called the two-way ANOVA model. Two-way because we're dealing with 2 factors. See, there's the model factor that goes this way. There's the land water factor that goes that way. So this whole ANOVA test fits into this thing called, the F-test fits into this thing called the K-way ANOVA model. And it's just one model, one test, and it answers all your questions for you. For this particular example, if you go look at the R code, it'll give you a really small p-value for the NWP differences. So you say there is an X1 effect. But for the land water, it says no, p-value is big. I don't see much difference. So we say there is no X2 effect. Okay, there's the jargon. Now, making things more realistic, suppose we don't have many numbers, right? We don't have 3 numbers in each of these cells. Suppose there's only 1. So 1 skill score for every one of these 6 runs. Well, okay, there's no free lunch. If you don't have money, resources to get more skill scores for each of these scales, well, you can't do any tests. I'm not going to sell you anything that can't be done. There are no tests. But you shouldn't just give up. You can still use all this machinery we're talking about, the ANOVA F-test and whatnot. All you have to do is to make assumptions. which is fine. There's nothing wrong with making assumptions as long as you say in your paper, assuming blah, I say this. No reviewer can reject you. You made the assumption. It's good. It's like making a disclaimer. It's fine. So in this case, I can assume, for example, I'm just trying to show you, you should relax and learn to play with data. Assume there is no land water effect. Okay, just make that assumption. So if that's true, then you can lump these two numbers together there. You can lump those two numbers together there. And we are right back in the realm of the first example where we can do a one-way ANOVA to see if there's a difference between the three models. And again, you can go to the R code example. You'll see it says, no, there's no difference between the models. As an exercise, you don't have to do it now. You can say, well, let's assume there's no difference between the models and see if there's a land-water effect, if there's a difference between land and water. Okay. You can lump the numbers together differently, do another F test, and that'll give the answer. Okay. As I say, the moral of all of these examples here was to use the F test generously. Okay, and here is the R code for all of those examples that I was talking about. R code explanations and everything. One more thing before we go into the second part of the talk. Let's back up to one of these examples. Okay, I don't know. Let's go back up here. Let me clean this up a little bit. Okay, clean. All right, so we have two factors. We want to see if the models are different, ANSEP, WRF, COAMPS, and we want to see if there's a land-water difference too. Well, there's one more thing we forgot to ask ourselves. What if there is a model difference, right? Like ANSEP is different from WRF, but only on water, not on land. It's a possibility. So you notice I'm not talking about if there's a difference in the skill scores between land and water. I'm asking about whether there's a difference in skill scores between ANSEP and WRF, but on two different levels of the other factor, on land and on water. So if there is a difference, right? So if there's a difference between ANSEP and WRF on land, but not on water, the word, the jargon that describes this scenario, this situation, is interaction. And my pen just died. Let me reboot quickly. So once I'll keep talking to buy myself time here. So one says, so if the model effect depends on whether you're on land or water, one says there exists an interaction between X1, X2. So X1, remember, is our NWP factor. X2 is the land water factor. Good. All right. So what about this interaction? Can we answer the question, is there an interaction between models and land water or season or whatever? Well, the beauty of this ANOVA F test is that answer falls out of the same ANOVA model we were talking about. So for example, when you look at what comes out of ANOVA model, right? So this p-value here is small. It tells you there is a difference across the levels of X1, so the three different models. This p-value is big, so it says there is no difference across the levels of X2, so there's no difference between land and water. And there is the interaction term, okay? So it even gives you a p-value, and in this case, the p-value is big, so no, there is no interaction between the two factors. Okay, so you can answer the question of whether there's an X1 effect, difference between NWPs, X2 effect, difference between land water, and an interaction between them, all with one approach, which is this thing I'm selling you, the K-way ANOVA F test or model. And it gives you F tests. Okay. So in this case, for our example, no interaction effects because the p-value was big. In the version of this talk that's on the website, don't worry, things are much more legible than what you see here. Okay. So this was part one. Any questions? Don't chat, speak up. The chats we can do later. Okay, no pressure. If you don't want to speak up, we can chat later. Okay, no pressure, no pressure. Maybe I'm putting too much pressure. All right, let's go. Part two. Okay, so here we are again. Let's take three factors. Here's our NWP factor. Here's the land water factor. And I forgot what X7 was. What was it? Let's see. X7 factor is pressure levels. Okay, suppose it's got three pressure levels. We'll get there. Consider this your break. Scrolling back and forth. Okay. Levels. Pressure levels. Okay. And again, we want to answer the same question: is there a difference across models? Is there land water? Is there a difference between pressure levels? All that stuff. Well, do the counting again. So don't just barge in there, start answering questions. Do the counting before you go. You need to go do 30 runs. Why? Because there are 3 levels of X1, 2 levels of land water, and 5 levels, pressure levels. That's, if I've done my arithmetic right, yeah, there are 30 different runs, 30 different scores you need to get. You won't be able to, don't even try, right? It's pointless. So stop and let's think. This is where you need to start thinking, remembering this talk and thinking, oh yeah, Caren said something about how we can reduce the number of runs. Well, let me tell you. Yeah, okay, for the sake of time. Yeah, okay, let's say this. Mathematically, that's the problem with math. Mathematically, there's no problem. We can do things. If you had these 30 scores, you can, again, throw them into that R code I've provided you, and it'll tell you everything you want to know. It'll tell you what the X1 effect is, X2, all the way to X100. It'll tell you the interactions. Each one of these things will come up with a p-value, right? Mathematically, not a problem at all. Okay. These are really, really high order interactions. That's what they're called. There's really no physical interpretation for them, but they're mathematical possibilities, so I've put them there. And the model will handle it, the ANOVA model. It'll tell you, yeah, there is an interaction or 10-way interaction or not. But practically, as I said, we have a problem because this number here is too big. What are we going to do? Okay. The first thing we're going to do is to reduce the number of levels that each of these factors takes. Okay, from 5, like one of those had 5 levels. No, bring everything down to 2. Okay. By the way, the reduction in the number of runs that will occur when you do this is not the reduction of runs that I'm advertising here. Okay. This latter reduction on the number of runs is much more fantastic, and it's going to happen in a minute. Okay. This is just an example I'm using to illustrate this whole idea of how to reduce the number of runs. So suppose, for simplicity, okay, it's an example. For simplicity, suppose all of the factors are binary. They take 2 levels, yes, no, land, water, high, low, hot, cold, whatever. I'm just going to denote those as -1 + 1, and I'm going to call them low, high. You have now stepped into what's called 2 to the k factorial designs. That's the jargon that describes this problem. The number of runs is still huge, right? If you have 8 factors, like in our example, there's still 64 runs you need to do. Okay, that's still a lot. The question is, how do we reduce this? Let me show you. Okay. I say, let's take again as a concrete example, 3 factors, X1, X2, X3, and I say there are 2 to the 3 runs, and I've written them all out for you. You see them? Okay. Here are all the cases where you went and set the NWP factor to, let's say, NSEP, and then you set the NWP factor to WRF, and then you changed X2, this is the land water factor, to here is set to land, here is water, and then the third factor, whatever it is, just keeps changing. Okay. Every one of these things is a run, and you get a skill score for it. So you go pick NSEP on land and set X3 to, I don't know, hot, and run your analysis and get a skill score, 130. Okay. So there are 8 runs, 8 skill scores that you need. Now, even this is too much, but wait, I'll tell you how to even cut this down. Wait, how are we doing on time here? Okay, you're good. All right, so let's bring this effect jargon back in place. We want to know how much does the score change as you change X1? So how much the score change as you go from NSEP to WRF? How much the score change as you change X2 from land to water? And what is the interaction effect, right? All of these effects are things we can compute easily. Let me show you. The math behind it is truly first grade. Okay, here it is, the same data I just showed you above, and we want to find the X1 effect, right? What the difference between NSEP and WRF? Well, easy. Here is NSEP, or WRF, one of them. Here is the other one. So all you need to do is to take the mean of these scores and the mean of these scores. Okay, here's the mean of skill scores when you dealt with NSEP or WRF. I forget which is which, doesn't matter. Okay, let's say WRF. The order doesn't matter. So this is the mean skill score for WRF. This is the mean skill score for NSEP. The difference, whatever that number, an interesting number, okay, that's the effect. Okay. It's a difference between 2 skill scores, right? So, but it tells you what the effect is. We're not going to test to see if this is really 0 or not. Okay, that we'll do in some future talk. But right now, all I did was to show you how to get an effect. We can get the X2 effect similarly. Now you need to go take all the places where X2 is minus, right? Take the mean of those 4 numbers, and then take the mean of these 4 numbers when you're on water, land or water, and the difference is the land water effect. Good. So do you see how kindergarten-ish all this is? We're getting numbers, effects for every one of our factors. The one for interaction is a little more complicated. We don't have time to go into the details, but again, it's a difference between effects, the difference between skill scores. Okay, it's a different combination of means. But suppose you've now done all this calculation, and here they are. I've summarized, not all of them, but I've summarized some of them for you. Now, we have a bunch of effects. Right? So in theory, if we did all these 8 runs, we could answer all of our questions, and they're all sitting right here. The effects, good. But remember, we can't run all 8. I'm assuming we can't. We want to reduce that number. Let's play. Suppose we have money to run only half of these 8. In other words, 4. Heck, it could be worse. Suppose you don't have money for a half. Suppose you have enough money to run only a quarter of these 8 runs. Okay. We have now just stepped into the realm of what are called incomplete 2 to the k designs. And if you're running only a half, then we're running 2 to the k half of those. So that's 2 to the k minus 1. If you have money for a quarter of the 2 to the k runs, that's 2 to the k minus 2. And you can see where I'm going with this. All of these, this whole incomplete blah, 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 they're also denoted or called 2 to the k minus p designs. So when you see 2 to the k minus p design somewhere, you're looking at somebody didn't have enough money to make all the runs, and they're taking 2 to the p fraction of their runs. Okay, so let's specialize to a half just for fun. and you'll see what happens. Suppose I have money only for this half here. So these four. Okay, why did I take these four? For no particular reason. You didn't have money to run all four, so you got all eight. So you got these four scores, and now you're out of money. You say, all right, let me go start computing my effects. Well, I gave you the formulas for computing all the effects, just a bunch of differences between means. I'll leave it as an exercise, like they say. If you go look at those effects and look at the differences, you'll see something not so good. You'll see that they're all the same. What you get for the X1 effect, the NWP factor, what you get for the X2 effect, land water difference, and for the interaction, they're all identical, same numbers. Okay, this is bad news, right? Because it can't be, right? How can it be that all the effects are equal? No, what's happening is, okay, I'll tell you in a minute, but the word that describes this situation is called aliasing. Okay, that's the big word here. When three effects are equal in an incomplete design like this, one says that those effects are aliased. And another thing that people do in this business is to write things like this. It's called an alias structure. See, it doesn't really mean anything to say x1 equals x2. They're factors. How can they be equal? What this really means is that the effects, it means this, right? That the differences that you computed are all the same. Okay. Now, one more thing before I give you the punchline. You knew there had to be a theorem here, and there is. I don't have time to prove it, but let me just give it to you. It turns out if three effects are aliased, like in this case, x1, x2, x1, x2 are aliased in this incomplete design. What that really means is that if you were able to go do all 8 runs, 2 to the k runs, and compute all the effects, you would notice that what you've computed here for the x1 effect is actually the sum of those effects. Okay, to be specific, for example, when you compute an x1 effect in our incomplete design, and you get a number like minus 54, and you say, okay, that's the effect. What you've really computed is the sum of 3 effects in the whole complete design, which we don't have. Right? We don't have money to get it, but this is where the theorem is useful. Okay, so that's the bad news. So when there's aliasing, you think you've estimated the NWP effect. Well, you haven't. You've estimated a combination of the NWP effect and the land water effect and the interaction. Okay, so that's bad news. But there's a good news. The good news is that if you take a different half, now I'm not saying go back and do another half, then you might say, well, I just ended up doing all of them. What are you talking about? No. Back up. Let's just think it's a thought experiment. Take a different half of the 8 runs. You're going to find out that different effects are aliased. For example, x1 and some 3-way, that's what this is called. The 3-way interaction is aliased. And x2 and x1, x2, x3 are aliased. Well, you might say, okay, I haven't gained anything. Why is this good? What's good is another thing, another theorem, principle, if you will, that high order interactions, 2-way, 3-way, 4-way interaction, generically they get smaller and smaller than the main ones. These are called main effects, x1, x2. This is an interaction effect. Interaction effects are generally smaller than main effects in magnitude. They are. So what that means is when we estimate x1, this combination, which is what we can do in this incomplete design, you have actually approximately estimated the x1 effect. Why? Because this is much smaller than that. This is much smaller than that. So even though you're estimating a linear combination of effects. One of them is much smaller than the other, so you have essentially estimated the two effects you were interested in. Now, believe it or not, this was the punchline. I have one more slide to wrap things up, but if you blinked, you missed it. So let me summarize it again. We managed to estimate the X1 effect, right, whether there's a difference across the NWPs, and the X2 effect, whether there's a difference between land and water, with only half of the 8 runs, with only 4 runs. Okay. We managed to do it by thinking about this aliasing and then taking a special half that makes sure high order interactions are aliased with low order things, because then we can ignore one relative to the other and we're done. Okay, so to bring this home completely, going back to our example with 8 factors, remember that we had to run like 3,000 things. Well, if you take this aliasing business, and if you go look in the back of textbooks on experimental design, they'll tell you, okay, they formalized, this was just an example, okay? They formalized these things and the theorem and everything that I've told you about, and they figured out specifically the runs you need to make to get the effects that you're interested in. If you want to estimate X1, X2, X3, and you don't care about interactions, the back of the textbook appendices tell you, go run this, this, that. Okay. For example, let's be specific since I am running out of time here. Okay. So let's go back to our example. 8 factors, NWP, land, water, season, all the way down to station. So the back of the book tells you this table that I've reproduced for you. Okay. So what does this mean? This is how you, what you do. You say, all right, the first thing I need to do is to go set all of my factors to their low levels. So you set X1 to whatever the lowest one is, let's say NSEP. Okay. You set X2 to land. I use low and high as just placeholders for the 2 levels, right? It doesn't really mean low and high. And season, you set it, so you set everything, you set all the knobs on these 8 factors to the 1 level, okay? And you run, you get one skill score. Score 1. Then you go back and do another run where you leave those 4 the same, right? It's very non-trivial, extremely non-trivial, but you switch the other 4 factors. So if this was NSEP, now you switch to WRF, okay? But leave these 4 the same, etc. And run, this is run 2, you get another score. And then go through all these different runs until you come to run 16. And run 16 says, okay, now completely flip everything compared to this first one. Look, we've completely flipped everything. Let me skip to my color scheme here. Okay. So you get another score, score 16. And now you'll just have to take my word for it. If you go back and use those formulas that I gave you for computing effects, differences between mean scores, and with just these 16 runs, you can estimate all the effects that you're interested in. Right? You can see if there's an NWP difference, you can see if there's a land water difference, you can see if there's a seasonal difference. You can see all of those with just 16 runs. 16, right? That's the number of columns in this table, compared to the 256 runs that you would have had to perform if you didn't know about this experimental design stuff, if you didn't know about these appendices in the back of tables, in the back of books, or wired into experimental design software. Okay. So yeah, this was it. We just reduced 256 to 16, and now we can estimate everything we want. And this whole experimental design methodology even tells you which runs you need to perform precisely, which combination of settings you need to do to be able to get all the effects of interest. I'll close with this: the reward, the punch, the return on this whole methodology, on this experimental design methodology, is larger and larger the more factors you have. Okay, so for example, with 8 factors, which was the example we did, this table here, this is again a table that appears in books and stuff, tells you you need 16 runs. Okay, and those were the 16 that I just showed you. Okay, if you have 15 factors, it's not a very large number, but if you want to answer all the questions of interest, ordinarily you would need 32,768 runs. Okay, it's 2 to the 15. But using this methodology, you go look in the back of a book and it tells you, no, you only need 16 runs, and it'll even tell you which 16 runs you need. Set factor 1 to blah, set factor 2 blah, set factor 4 blah. It'll tell you all of those things that you need to know. Okay, so huge reduction from 32,000 to, again, 16. 16, it's not always 16, right? I mean, it depends. Sometimes it's 64 or whatever. Again, it's all very non-trivial, non-intuitive. But it all falls out of this experimental design methodology. So in conclusion, in part 1, I hope I convinced you to do t-tests like Ian told us, Professor Joliffe, but don't do too many of them. Instead, do this one-way ANOVA F test we were talking about. Okay, the needle in the haystack test. And I've given you the code for doing it. It's up there. And in part 2, when you're getting ready to do a verification and you want to start comparing things, don't just barge in there, because you're going to run out of money. You're not going to be able to make all the comparisons you want, even compute all the scores you want. Stop and think in terms of this experimental design stuff. Go look in the back of the books, decide which effects you do care about, which ones you don't care about as much. Look in the back of the book. It'll tell you which models, which seasons, which settings you need to run. And then you can use this methodology to answer your questions. In a future talk, we can talk about how to put these two things together. So you can also do significance tests on these magnitudes that you've estimated using this methodology that we're talking about. But that'll be a future talk. And I shall stop there for questions. Thank you.
Thanks very much, Caren. Very interesting perspective. I think we already have a number of questions, starting one from Barbara. Barbara, want to say your question yourself, or want me to read it?
Yes, I have actually 2.
I can read your question, believe it or not. Do you want me to read it, or do you want to...
I can verbalize it because it's,
okay,
it's
go ahead.
more than just what I wrote there quickly. So you show the table with the 16 experiments, and it starts with the -1, and then every time you switch a little bit.
Yeah.
So yeah, exactly. This table that I lost.
You want to look at you want to look at the big one here, plus minus table.
Yeah, that one.
Yeah.
Okay.
Yeah.
This works when you have factors with only 2 levels, right?
Yes, that's 2 to the k. There are factors for 3. Journal is crashing. Do you see the crashing window in front of you? You can't see it. Well, not a problem. Not a problem. Okay, hold on. I know what to do.
But it's okay. I can ask the question even without
Wait. No. Wait. It's not as bad as one might think. Okay, so I can answer your question if I may be so bold as to anticipate. This is called 2 to the k design, 2 to the k minus p, because we took a fraction, but there are tables similar to this for 3 to the k, 4 to the k, and any combination of things you want. In other words, each of the factors is allowed to take 3 levels. Each of the factors is allowed to take 4 levels. Even combinations, you can have 2 levels in 1, 3, just like the example we talked about above. You can have different number of levels for the different factors, but there are methods that will tell you how to set each one of those things and go get your runs and make your comparisons. It's just beyond the scope of this lecture, but you'll find them in books, you'll find them in software. It's all been worked out.
So,
Did I
but
answer
this, I'm trying to think about an application in
Sure.
the modeling world, for example. If
Yep.
I have different schemes to test and see if there is a difference in the output of the models, that's what I do. So I put, like, say I have 2 different you know, like compaction schemes. I put one, put the other, boom, score, and you know, and use this type of experimental design to for the runs. That's
Yes.
one application.
So absolutely. If I can get my page to go all the way up to the top. In one of the first examples, one of my own first papers where I used this methodology, I have many factors in there. One of them is multiple models, but one of the other factors is, the Kane-Fritsch trigger, whether there's a Kane-Fritsch trigger or not. Another factor was, again, I'm using these words not knowing what they really mean. I'm not a meteorologist, remember? The other one was whether the radiation component of the model was, you know, some set of authors version versus some other authors versus some other. So yes, there were different settings, different model parameters, NWP model parameters that I was setting things to and running that model and getting a score and making the comparisons. I used this very methodology here to do that experiment.
Okay, and I have a second question, if I'm allowed.
Yeah,
When you show the 3-dimensional plots, where you have the you were talking about the ANOVA, and there we go. So what I'm trying to question to myself is if the ANOVA, essentially, for every one of these levels on this this is a 3-dimensional space because we have 3 factors, right?
Correct.
So if you have 8, you have 8-dimensional space, and you plot points, okay, in this space, okay, and you have a bubble, okay. So in the moment in which you have some dimension to this bubble, there you have that essentially, for example, if you have a 1-dimensional towards land and water, it means that the scores for the land and the scores for the water are different. So in that moment, you know that there is essentially you should stratify your verification for these 2 levels in this factor. So that's what the ANOVA does. It looks at is an analysis of variances in this n-dimensional space. Correct. And where you have a variance that is beyond the 0-dimensional point, 0-dimensional object, then you have a stratification. Then you can identify how to stratify your verification, for example.
Correct.
So this can help in choosing on what to stratify.
The ANOVA part, if you have, okay, so remember to run that ANOVA model. So we use model for so many different things here. So to run that statistical model we call ANOVA, you need to have all the necessary skill scores we talked about to be able to estimate the effects. And then, like you said, to decide how to stratify, right? That was the topic of part 1. But in part 2, I'm saying, all right, suppose you don't have all the skill scores necessary for even running the ANOVA model to be able to tell what effects are, because you need a certain number of, you need to fill up enough of this space here, this 3D space, to be able to run an ANOVA model to get the effects that you want. In part 2, what I've shown you is, indeed, you don't need to run, you don't need to fill this whole space. There are certain points that you need to, you can take special points that this whole methodology tells you. You can take them, cherry pick them, just run those. And now you'll be able to run ANOVA model and estimate all the effects that you want.
Okay, thank you very much.
And then you can go on and stratify further, because now you've got the ANOVA model running. You can stratify further to decide exactly which comparisons are meaningful, which are not, whatnot.
Okay,
Good.
Thank you. I think Marion's comment has already been addressed, right, Marion?
Yeah, I think it was very similar to what Barbara was saying, but it kind of forgot about this stuff because I know it's there, but it kind of comes around to the fact that we produce these massive scorecards with, you know, a load of scores on them. And we do that for each configuration, say, that we're looking at. And then at the end, we're still going to ask the question, well, which one of these is actually better? And that's still an impossible task to do without some sort of statistical handling. And I really think this is the way one can, you know, get a handle on it and see what happens, really. Yep. I'm sure Barbara's in the same position. She'll have a wealth of possible data sets to try this out on to see what happens. Yeah? She's nodding. Okay.
Good.
Okay, so Ted, want to verbalize your...
Sure. I was just wondering if it's somehow related. I was saying to the Yule-Simpson effect. I know that's for continuous and correlations, but you're sort of deciding your step one. I mean, it feels to me like you're trying to remove potential confounding factors to decide how to stratify, and then step 2 is the quantification of those linkages that are hopefully more causal or more interpretable or more. Is that the right way to think?
That's correct. That's correct. The word you used, confounding, to unconfound things. In experimental design, the field of experimental design, those two words, confounding and aliasing, are similar, but they're different.
Yeah.
Okay. So, but as long as we're outside of that realm, we can use those words interchangeably. So you're right. This whole methodology allows you to determine which factors are confounded with each other.
Yeah.
So you can't estimate them separately. And then the methodology is turned around into, well, this defect is turned around into a methodology that then tells you, if you go pick these runs, you can deconfound, and the term is de-alias, the effects, and get all the ones that you really cared about.
I mean, and of course you're dealing with discrete kinds of things, so there's no, you wouldn't do a correlation because you're, model version A, model version B, stuff like that, right? So it's a nonlinear framework for all this.
Correct. That is one thing about this whole experimental design business. The variables, the knobs that we're turning, are categorical.
Yeah. Yeah.
So the only continuous variable here is the score itself.
Yeah. Yeah.
It's similar to regression, like one of these equations I wrote. Let me see if I can.
Yeah, it's like a categorical form of.
Correct. It looks like regression, and in fact, the math turns out to be similar to regression, but it's not because
there's
somewhere. But anyway, the fact that the factors are categorical, yeah, I can't find it.
I think there's a bit of a parallel possibly with causal networks. I don't know if you follow that, because you often go through a first step where you try to see where you have conditional dependence between the different causal factors, and you peel away and just focus on the ones that are left, and then you quantify the effects after that. So it seems some sort of, so maybe just to I think there is some growing use of this in the climate community. So maybe but Barbara Brown has asked about whether modelers might be more receptive to this approach. Maybe. I mean, if they run into walls, that's a better time to talk to them about trying something different. And I think a lot of modelers are running into walls.
Just a comment about the causal modeling that Ted was talking about. There are similarities between the methods used in this business and in that business, but the similarities are similar, and mostly because they're both framed in terms of conditional probabilities. Given something, what's a probability of something else? And then you use Bayes' theorem to parse things out and condition differently and whatnot. But beyond that, the approaches and the goals are different.
Yeah, just that the logic seems similar in a way.
Logic is similar. Yes, you're right.
There seems to be a lot of interest in that. There are a few other questions and comments. Barbara Brown, would you like to make your interventions verbally?
Oh, oops, sorry. So I just mentioned that I tried to push this idea probably a decade ago with a modeling group here at NCAR, and it went nowhere. They just said, no way, we know exactly what we need to do. And so it was a frustrating experience, but I think this is a great idea, especially because, you know, we get overwhelmed with all these modeling runs that, you know, really are hard to sort through and figure out what is the real signal there. And this provides an opportunity to find that signal in a clear way. So thanks, Caren, for talking about this today.
Yeah, thanks. I've been spreading this news for about a decade now. I have a few papers written on it, given a few talks on it, and now thank you for letting me talk about it to our next generation of students. Hopefully they're going to take this word and spread it further. But your observation is correct. Every time I've written a paper, the reviewers, the ones whom I could tell were modelers, had your reaction that, look, we don't need to do all this. I know what I'm doing. Well, part of the problem is modelers are too smart for their own good. They're sort of like physicists. They think they can do everything on their own. They don't want to borrow anything from any other field. But I've managed to turn a few modelers around. You know, they joined me on those papers. When you do have lots of factors, lots of comparisons, and you start pointing out to them that, look, you're, to use Ted's terminology, you're confounding lots of different things here, they start to get it. It takes time.
Okay, thanks. I think we have more hands. Start with a hand from the students. Gita Main, would like to ask her question?
Yes. So I really love the overall, like the first part, but I got a little confused in the second part where you were having 4 experiment in X1 and 4 experiment, like it's like for NCEP 4 experiment and for WAR 4 experiment. So I got a little bit confused why like 4 experiments in.
Okay, so let me see, where did I have 4
Like the
experiments?
same screen you were showing the last time.
Let me start sharing again, and you can take me to the page where I.
Yeah, this one, the same screen, yeah. I
Oh,
think.
okay, this one right here. Okay,
Yes.
so let's start with the simple one here. So we have X1 is my NWP factor.
Yes.
So it takes 2 levels, let's say NCEP and WRF.
Mm-hmm.
X2 is my land water factor. So it takes land and water. And X3, I don't know, let's say it's season, and let's say it's hot and cold. I'm just making up factors here. So what this whole table means is, all right, I need to take NCEP. So that's when X1 is set to -1. And then I need to set X2 to -1, land, and X3 to hot, let's say. So I'm going to run NCEP on land on a hot season, and I get one skill score. Then I need to stay with NCEP and on land, but now go to a cold season. So I get a new score. I still stay with NSEP, go on to water. See, I changed from -1 to +1, and back up to hot season and get another score. Now stay with water, stay with NSEP, go to cold season, get another score. Do you see what's happening?
Yes.
And
I think
then I finally give up NSEP, switch to WRF, the other level of X1, and then repeat these 4 settings. So the 4 you're talking about are basically 2 to the 2. And it happens because each of these 2 takes 2 levels.
okay, understood. Thank you.
Makes sense? Good.
Okay, we have a hand of Laurie Wilson, please.
Yes. Well, throughout pretty much the whole lecture, very interesting talk. I was, of course, thinking about how this might be applied in the projects we have that are going on now. All 4 projects involve 3 models, so we have a model factor for sure. I think 2 of the projects involve data from different locations, different stations, which basically would be considered together in the overall results, but that could be another factor, I suppose.
There it is, X8, station factor.
Right.
Oh,
So-
sorry, I'm not sharing my screen. Never mind. I said there it is and you can't see. So here, there it is. Station.
So this would just be equivalent to taking the samples that we have on the model runs and stratifying on the basis of those variables, right? The models and stations, and then calculating scores separately for each subset of the data set. And then
Well,
we have
if
the
you-
scores.
Yeah, again, so remember, if you can compute all the scores for all the combinations we're talking about of the factor levels, then all I'm advocating here is not doing too many t-tests and relying on the ANOVA F test to test the significance of the comparisons you're making. And part 2 of the talk, sorry if I'm repeating myself, but just to make sure, in part 2 of the talk, I'm saying, suppose you cannot make all the combination, you can't run all the combinations that we're interested in. Then these books can tell you which combinations you can run to still be able to answer your question.
Okay.
So
So
it's all about taking different combinations of these factor levels.
So I guess my question then is since data from different locations that aren't very far apart are going to be correlated with each other, maybe quite a bit correlated with each other, how does that affect the
Good point.
application?
So in part 2, in part 2 of this method, remember I didn't do any inference at all. There were no p-values, no confidence intervals, nothing. All we're trying to do in part 2 is to use this methodology of experimental design to be able to come up with a point estimate of the difference between 2 skill scores. So if they are correlated or not is something that will be it will be important if we're doing tests, right? If we're doing p-values and confidence intervals and whatnot, because that's where independence comes in. In this case, if two stations are nearby, well, you're just going to get similar effects. That's that. So in short, spatial correlation or temporal correlation, all of these correlations that we usually worry about when performing tests don't come into this because we're not doing any tests.
Okay, good, thanks. But I presume that then we can think, well, okay, the models probably are pretty independent, so we could go ahead and do the tests and not worry about correlations too much.
Right, so that will be the topic of this 3rd talk that I said I will give in some imaginary time, where you will be testing the significance of the effects that we're getting in this reduced way of getting data and whatnot. It gets more complicated, and the math isn't as simple as it is here. You really need to rely on software to do the calculation, but the framework is there.
Okay, I think we are running a bit over time, but I'd like to give the opportunity for at least one more person. Mosh, Arno, you have two questions in the chat you'd like to verbalize.
Yes, I can. So I think one of them was just answered regarding non-independent stations, for example. The other one is you showed in your table that if we have if the 2 to the power of k minus p is when k is 15, it is smaller than when k equals 10, for example. Would it be worth using like artificial factors to reduce the number of runs that we need to have?
Okay, so sorry, I missed that. So we're talking about this table. So
Yeah.
walk me through your question again.
So when I look at k equals 15, I see that we only need to make 16 experiments.
Correct.
But when I look at, say, k equals 8 or 10, I see that we have to make more than 16 runs.
Oh, I see. So you're wondering if there are times when you're actually better off to have more factors in your problem,
Yeah.
so that you can get away with fewer runs.
Yeah.
Yes, that is true. Okay, and it, as of course, you want to make sure that your factors aren't. I mean, we can't just throw garbage into the analysis and expect to get useful things out.
Yeah.
Especially because we're not doing statistical tests here. There will always be an answer that will come out of this methodology, and you won't know if it's right or wrong because we're not doing tests. But as long as you use factors that you believe are relevant, yes, there are advantages to having more factors in there. In a way, it's intuitive. It makes sense. You're providing more information to the problem by providing another direction in this multidimensional space that we're moving into. So you get a better feeling of what's going on in this whole big space by having more factors. Yep.
Okay, thanks. So where do we start?
When do we start, or where do we start?
Where?
Where?
Yeah.
Okay, clarify a little bit for me.
So is there a recommended book or a website?
Oh, topic. Yes, the classic book. Yes, the classic book. Montgomery. And it's called Experimental Design.
Oh, I just put something in the chat saying I would come up with a list of a variety of books that we could include, but that's I don't know that one, Caren, so I'll have to look at that one.
It's the oldest one. It's equals 0.
Yeah.
And it's up to its 8th edition, and I'm still using it in my experimental design class. There are a few others that are better. I shouldn't say better, different. Okay. But in my case, again, I have my inertia for having used this book for years, so I'm staying with it. But so perhaps it's better to go with one of Barbara's suggestions to break out of my bias and my history, start fresh.
So I just want to say that some of those books are pretty daunting. So finding something that's accessible is I think something we should try.
That is true. Books on you're right. Books on experimental design are not very friendly.
Yeah.
Generally, they're of biblical proportions, and the thin ones are way too mathematical and much less useful. I can find some compromises, and I'll check your list, Barbara, and if I can find something else, I'll add something else.
So one thing to mention too is this is one of the history of experimental design basically goes back to the very beginnings of statistics with Fisher and people in the early part of the 20th century. So it's a fundamental part of statistics that
and for some
meteorologists haven't adopted yet.
And for some reason, it has fallen off of even the general curriculum for stat majors. It's one of the last courses they take before leaving. It's ironic, but yeah. The reason for that is because stat departments have become more theoretical in nature. But this experimental design is all grounded in practice. How do I do things is the question. So it's mostly in engineering, industrial engineering, and now I hope in environmental circles where people talk about these things. Practical circles.
Okay, thanks. I think Ian Jolliffe also made a comment about book. Would you like to say anything about that, Ian?
I'm curious, what are these books you guys are suggesting? Let's see. I can't move my chat window. Go ahead,
You're
Ian.
muted. You're muted.
Ian, you're muted.
Okay, got it. The book that I mentioned I found on my shelf is actually called Applied Linear Statistical Models, and is about 1,500 pages long. So it's probably not at the most mathematical end of the spectrum. It's somewhere in between. But since then, I found another book on my shelf, and I don't know whether you can see that.
I can't see the authors. Who are the authors?
It's Bob Kempson and Jeff Clark.
I'm not familiar with that one. Okay.
It's quite old, so I don't know whether it's still in print. Jeff was someone who taught me. Bob Kempson was someone who I supervised for a PhD. Sadly, they both passed away.
Oh.
But this, as it says, is Introduction to Design and Analysis of Experiments. So it might be a useful level for people in this group, if you can find it.
I'll check it. I would be surprised if it's any more introductory than the Montgomery book I mentioned.
Yeah.
The Montgomery book is pretty much where it zero. It's as introductory as one can get without math. But I'll check it.
So many books on my shelves that
yeah.
I didn't know what I had, but I found those.
But going back to your first book, the linear model, the 1,500-page linear model book, does it go into experimental design, or is it all about linear models?
Yeah,
that's another thing that
half of it is on experimental design.
Good. Yeah, those two generally do go together, linear model and experimental. So it's generally, the books are generally split between those two. Yeah, good. So that will be a good compromise, which is what I did in my talk too. There's the linear model part and then the experimental design part.
Yeah.
Yeah.
And the authors on that, Anita Kuttner, Nachheim, and Wasserman. I don't know whether I can.
I thought I was old, but none of those names ring a bell. So they must be way before my time. Okay. Yep, don't know them. Good. Okay.
Okay. So thank you very much. And the final comments we have is from Ted about this approach could be useful for determining what is being called the emergency constraint in climate literature.
Yeah.
Okay, that one.
Well, we discussed this briefly at the drop-in session. There's this in the climate science area that's been, if you just, I'm sure it must be Googleable at this point. If you just what's called emergent constraint, which is a relationship between an observable property of a model, it could be the seasonal cycle of the sea ice or something like that, and the projection of the response to climate change. So it's a correlation. It doesn't have to be linear, of course, but it's generally a correlation across models, and you're basically looking at the correlation of two different properties of the simulations, but one is a short-term property and one is a long-term property across models. And I guess that must be, you must be able to cast this into this framework, I would have thought. At the moment, people are just fishing around, p-hacking, well, I shouldn't say that, but there's if the result gets published, there's a very high probability that within 5 years it's going to be shown to be false, which is a pretty clear sign. So people, there's no structure to all this, and so it sounds like there probably could be. And
I haven't heard that phrase, emergent constraints. I'll go check it out. Thanks.
Yeah.
Okay, I think this is quite a lot. So I propose we close the session.
Thank you.
And we come back again tomorrow, right?
All right.
Yes, that's what you get when you have passionate people. You go over time. So I want to say thank you to everybody, and see you tomorrow. Tomorrow morning is the first lecture is a Ragu on extremes, followed up by a drop-in session. Okay.
Bye.
Goodbye, everybody.